And we're back. Welcome back from the weekend and happy Tuesday. Today we'll be switching gears and turning our attention to the material from Chapter 4, which concerns threading. Threading is probably one of the top 5 constructs in modern operating systems. But before we begin, let's turn our attention to some administrative bits. The reading has been updated by the 22nd of October. Please make sure you have read sections 4.0 through 4.6, pages 159 through 180, and section 4.6 in OS Concepts, pages 188 through 196. As usual, please make sure you're keeping up to date with the reading. It will be very important for your engagement with the material and your success in this course. So the objective of Chapter 4 is couple reasons to introduce the idea of a thread, which is a fundamental unit of utilization for the central processing unit. We'll talk about thread APIs. We'll explore a lot of strategies for threading. We'll examine issues associated with writing multi-threaded programs, and we'll also examine and take a look at operating system support for threads. Okay. So why don't we begin? Most modern applications are so-called multi-threaded, so they have many threads, and these threads run within the application or the process, which is your program in executable state. And these threads will handle multiple tasks for the application, and these threads might do things like update the display. Everything you see being drawn on the screen, for example, by a browser, that's done by threads. Maybe fetching data, whether that's from a disk or from the network, that's done by some threads. Spell checking in a document, that could be done by a separate thread. And also answering incoming data requests from the network or from across the network, that is also handled by threads. And so you have this coordination of different tasks, each one of which is performed by this thing called a thread. But we haven't yet talked about what is a thread. So let's take a look at these two diagrams. Now, direct your attention to this figure on the left, and this is in the book. And this is, let's set our pen first. Let's try blue. So I turn your attention to this diagram on the left, and this is in the book. This is a process. And we said the process has the text section, which is your code. Okay, check. It has your data, both your from the heap, the dynamically allocated data, check. It has file information, these file descriptors that describe all the file resources that you have open for your process. Okay. You also have these other pieces, and these other pieces, your register file, which contains temporary values where they're stored. The program counter, we said that contains the address of the next executable instruction, and the stack is where your automatic storage occurs. Things like your parameters, your return values, your local variables in your program are all automatically allocated by the stack. Now, these three things, the registers, the program counter, and the stack, those are associated with a so-called instruction stream. Instruction stream. And the instruction stream, of course, is just the execution sequentially of each one of those statements that collectively define blocks of behavior in your program. And so, of course, you need the program counter to know which address you're going to go to next to fetch the next instruction. You need the registers to store the temporary values for the execution of your instruction stream. And you also need the stack for the automatic storage, things like your parameters to functions, your return values, your local variables. And so each one of these three quantities are associated with the execution of instruction stream. And that's your quote-unquote thread of execution, which is noted in the book and several other places in the literature by this squiggly line. And so this process is sometimes called a single-threaded process because the execution of this process is only a single instruction stream. And therefore, we can say that a process contains a single thread. So let me direct your attention here to the right. This is also a process. Now, in this process, of course, we have the text section listing the code for the program. Those are the instructions. The data, which is the heap, that's dynamically allocated memory. And then we also have the files, those file descriptors, those file resources. Now, if we take all of that state or the context associated with the instruction stream execution itself, namely the registers, the program counter, and the stack, and we replicate it, well, here is one context, here's another instance of that context, and here's yet another instance of that context. So because we have now 3 copies of this collection of information needed for an instruction stream, the registers, the stack, and the program counter, this means we can have 3 instruction streams, whereas before, in this figure on the left, we only had 1. And so therefore, we say this is a so-called multi-threaded process because this process can support 3 different instruction streams. So what does that mean? It means that one of the instruction streams could be instructions dealing with updating the display. Another could be getting data from the network. And yet another could be reading from disk. And this all happens, quote unquote, at the same time because each one of these instruction stream executions is happening at the same time. Okay, so why do we have threads at all? Well, process creation is very heavyweight, but thread creation relatively is very light. And what happens when you have processes? Well, here's one process, and what if we kind of draw what looks like a stack of cards here? Here's another process, and here's another process. So in this case, we have 1, 2, 3 processes, and if we were going to invoke these 3 processes, there's a lot of information that we have to load both onto the CPU and off the CPU whenever we context switch between them. Now, certainly each process has its own single thread. There's the thread of execution for the first process, thread of execution for the second process, thread of execution for the third process. And we could certainly, as we saw with inter-process communication, we can certainly coordinate and send data back and forth between these 3 processes. So absolutely they could coordinate, but the problem lies in the context switching. For the context switching, we have to get all of this information, including the code, the data, and the files, off of the CPU or the current execution. And that can take a lot of time. Whereas if we're going to switch from one thread to the next, we keep all of this context, code, data, and file information on the CPU, and the only thing we're switching is between the register file, stack, and program counter for one thread of execution versus the second thread of execution versus the third. So it's a lot less information to switch between parts of the CPU instead of the entire CPU when you're context switching. And of course, context switching can also mean bringing that program from disk if all of the programs or processes can't fit in memory. And so threads exist because you can make your switching, your creation of these threads of execution much more lightweight. Rather than using a process each time, you want to engage in or instantiate a new instruction stream's execution. And you can also use threads to simplify your code and increase its efficiency. And it's important to note that most modern operating system kernels, they're generally multi-threaded in their implementation. This is so immensely useful. So when we look at servers, modern servers are implemented using multi-threading. So you have a client request coming in, and you typically have 2 categories of thread. One thread sits in a tight loop and listens for the incoming request. When it gets a request, a new thread is created in order to handle or service that request. But that original responder, if you will, that got the incoming request, it hands it off to a newly created thread and then goes back to listening for a new incoming request. So you can make this function of receiving incoming requests very, very fast and very, very simple. And then you can have multiple threads operating at the same time, one for the first request, one for the second request, one for each of, say, n many requests. And moreover, the context switching between these n threads for the first request or handling the first request onto the nth request is much more lightweight than if you had n many processes between which you were context switching. So modern server architecture uses a multi-threaded approach to their implementation. And so the benefits, there are multiple benefits. Responsiveness is a pretty important one, that you can have continued execution in parts of your program for some of the instruction streams if other parts are blocked waiting for things like I/O devices. This is very important for user interfaces. Suppose you want to update the drawing on a screen while listening for the mouse. Well, you have one thread listening for the mouse and the other thread doing the drawing for the update. So if some of those instruction streams are blocked, say this is blocked, your process can still make progress on the other instruction streams. So this idea of responsiveness is very, very important because it gives the user the sense that the system is doing something. That's really, really important, both for mobile devices as well as desktop and laptop type devices. Resource sharing. Threads can share resources of its process. We said those threads are a replication of that instruction stream context, the register file, stat, and program counter. And therefore, they share the same code, instructions, data, dynamically allocated memory, and the files. So all of these execution contexts, in this case, thread 1, 2, and 3, they're going to see the same code, the same dynamically allocated data, and the same files. So they can share these resources more easily than using IPC if they were threads within separate processes. And so this idea of resource sharing is much easier with a threaded implementation. They kind of get this resource sharing for free. Economy. It's cheaper than creating processes. It uses less resources, and therefore the context switching is much faster, giving you a lower overhead where you're not making progress on the CPU, a lower overhead if you have a lot of these execution instruction streams executing at the same time. It also gives you scalability. Now, this is a consequence of a thread taking up less resources. You can take advantage of multiprocessor architectures. There are some that will support natively threads on each core, and now you can physically have these different instruction streams, these threads executing at the same time. And so you have a lot of great benefits. Let's look at the idea of what happens in a multi-core system. Now, a multi-core or multiprocessor system, of course, multiprocessor, you have more than one CPU connected together via the bus. And in a multi-core, you have one chip, and on that chip is multiple cores or CPUs, if you will, on the same silicon. And so when you have these multi-core or multiprocessor systems, this puts a lot of pressures on the programmer to try to make use of all this wonderful, glorious hardware. It means multiple things, right? You want to divide up your program's activities so that you can have each part of your program execute on a different core or on a different processor. You also, this means that you need to balance out what things or what parts of your process or instruction streams are doing what. It might mean breaking up your data and scattering different parts of your data or pieces across different cores or processors, and then solving each piece in order to speed up, because the best way to make something faster is to divide it up into pieces and perform actions on those pieces separately. Data dependency. Maybe one piece of your program produces something that is needed by another piece of your program. So you need to look at whose results are needed by whom and when. And then, of course, the testing and debugging. If you have a lot of different parts of your program running on different cores or CPUs, you're going to have to keep track of all these things. How do you switch back and forth in a debugging environment? And so there's this idea of parallelism, and this is where you get your speed, and that's different from concurrency. Parallelism implies that you're going to be executing physically more than one task at the same time. And that requires having more than one CPU or core, each of which is running some different activity physically at the same time. So parallelism means physically at the same time. And parallelism is in contrast to concurrency. Now, they're often used as synonyms, but they're not synonyms. It's really important for this class. Parallelism is not equal to, that's a not equal to, concurrency. Concurrency means that you're supporting more than one task, but each of these tasks is making progress. And so that means if you have a bunch of tasks, 1, 2, and 3, then task 1 gets a little bit of time, then task 2 gets a little bit of time, then task 3 gets a little bit of time on the CPU, and then it goes back to task 1, then task 2, and then task 3, and so forth. And so with concurrency, while they're not physically executing at the same time, they're sharing fractional usage of the CPU, each one still is making some progress because each task gets a little bit of time. in some schedule. So let's take a look at other types of parallelism. There's one called data parallelism. In data parallelism, you're taking your data and you're breaking it apart and scattering those parts of your data, those pieces, to different cores or CPUs. And then the CPUs are running some sort of process or task on that data, and then the results are aggregated. Suppose you wanted to sort or find the minimum element in a list. So here's my list, and let's say I have n elements in my list. And let's just say, for the sake of argument, the minimum element, m, is right here in my list. But you don't know that at the beginning. So you take n, many items in your list of items, in an array, and then you break it apart. And each part is of size n over 2, for example. So this part here is also size n over 2. You break it into two pieces. And now, this is called data parallelism. You're going to find the minimum of each one of these sublists. Now, of course, there's going to be that same minimum in that sublist. And let's say we identified some other minimum in this sublist. We're going to call it m prime. It's not the true minimum, but it's just the minimum in that particular piece. Now that we find these minima, now we're going to take m and we're going to compare it to m prime. And whichever one is smaller, that's going to be our minimum. So m is going to be our minimum. And so that's data parallelism. We're breaking apart the data, and we're spreading subsets of the same data across multiple cores or processes and performing the same operation. And then we gather back the results. Now, that's exactly what Hadoop, which is an implementation of MapReduce, is doing. This is called the scatter operation. You perform a computation, and then you gather the results. And so the scatter-gather is exactly what Hadoop is doing, which is a big data processing framework. Okay, the other type of parallelism we have is so-called task parallelism. In this task parallelism, you're doing the converse. Instead of distributing the data across the CPUs, you're distributing threads across different CPUs or cores. And each thread is then performing a unique operation. Let me direct your attention down below. Here we have task parallelism, and you take core 0, 1, 2, 3, and 1, 2, and 3, for example. So you have 4 cores. And in this, you have a different task that's being performed. So maybe you have a processing pipeline, for example, for an image. The first one is going to change that image from color image to black and white. Maybe the other process is going to extract the edges, and then the other process is going to compute the histogram on those edges, and then the other process is going to compare it to something, for example. And so this task parallelism takes your threads, puts them across the cores, so there's a different thread on each core, and each one has a unique operation that they're performing on the same data. So in one, you're chopping up the data, distributing it. The other, and the task stays the same, and the other, you're keeping the data together, but you're distributing the task, and these tasks are different from one another. Okay. So as the number of threads grows, of course, certainly you need sophisticated mechanisms and APIs that allow you to support this threading. And so with increased number of threads, you also have support in the architecture of the underlying system for this threading. And so many modern CPUs have different cores, but they also have what are called hardware threads. And a hardware thread is nothing more than a native hardware execution of that context that represents the instruction stream, the program counter, the register file, and the stack pointer. And so these CPUs have hardware threads, so you're getting chip speed execution of instruction streams, i.e. your threads. And so the Oracle Spark, and Spark is Sun Microsystems, Oracle bought Sun, so now it's Oracle Spark architecture, has hardware threads, 8 cores for the T4. Each core has 8 hardware threads. And so if you look up the chip spec for the Intel i9 processor and the Xeon, you'll see in that specification the number of hardware threads that you have per core. And so here's an example of concurrency versus parallelism. In the top frame, and this is in the book, we have concurrent execution on a single core system. And so here we have 4 tasks, T1, T2, T3, and T4. And we're going to cycle between execution of each of these tasks, a little bit of time for T1, a little bit of time for T2, a little bit of time for T3, and likewise a little bit of time for T4. And then we're going to cycle back around. And so in time, every task is making progress where time increases going to the right. So here, we start executing T1, and then T2, T3, and T4, go back to T1, 2, 3, 4, 1, 2, 3, 4, etc. And so that's an example of concurrency. It gives the illusion that they're operating at the same time, but they aren't really running at the same time. They're just alternating with fractional usage of the CPU, and in doing so, each one is making progress as time continues forward. The second example, and I'll direct your attention to the figure on the bottom, is parallelism, and this parallelism is on multi-core systems. So that means physically these tasks are happening at the same time. So let's assume tasks T1 and T3 were on the first core, and task 2 and task 4 are on the second core. So here, you're going to share fractional usage of core 1 between T1 and T3. So we're going to have a little bit of time for T1, a little bit of time for T3, then T1, then T3, then T1, T3, and so forth, and so on. And on core 2, you're going to alternate, sharing fractional usage of core 2 between T2 and T4. So you have T2 gets a little time, then T4, then T2, then T4, T2, T4, etc. So this, you'll notice here, is the physical concurrent execution, or at the same time. During this time slice here, we'll call delta T, we have physically, during this time slice, we'll call delta T, we have physically T1 and T2 are both executing at the same time. Then we have T3 and T4 both executing at the same time. So this parallelism on a multi-core system, this physical execution at the same time versus concurrency with a single core, they are making progress together in time, but they give the illusion, but they're not actually physically executing at the same time. All right, and so Amdahl's law is a proportion that talks about the type of performance gains you can get by parallelizing your program. We saw that there's serial execution, and there's also having multiple processing cores. And of course, with multiple cores, you can chop a problem up and work on each piece and therefore speed up your computation. And so let's define S as the serial portion as a percentage of your program that cannot be chopped up or parallelized, and you have n processing cores. So Amdahl's law says the speed up is at most 1 over S, and this denominator S is the serial portion. You can't change that in your program, but you notice this denominator is going to change as a result of having your n many processing cores. And so what remains from the serial portion is the non-serial portion. That's that 1 minus S, and that's the proportion of your program that can be parallelized or chopped up or sped up based on these multiple cores. And so now, if you spread pieces of this non-serial portion onto each of these n many cores, that's going to be 1 minus S over n. And so what happens if n, the number of processing cores, is smaller? What happens? That means this term, 1 minus S over n, is bigger, and that means the speed up is going to be smaller because S plus something big is going to be small when you have 1 over that. But if you have a lot of processing cores, well, this 1 minus S over n, that's going to go to 0, and so you're going to get 1 over S as the ideal in terms of the speed up. And so that can be pretty significant, especially because your serial portion, S, if it's less than 1, of course, the speed up is going to be significant. So you can take your parallelizable portion of your program and negate or make negligible its amount of processing time in order to realize a speed up. Okay, and so an example given in the book, let's say you have an application and 75% of it you can chop up for parallel execution and 25% of it is serial. If you go from 1 core to 2 cores, this gives you a speed up by Amdahl's law of 1.6 times the execution speed. So as n approaches infinity, the number of cores, your speed up approaches or gets closer to 1 over the serial amount. And so the serial portion of an application, therefore, dictates the effect on performance due to adding more cores. So it doesn't matter how many cores you add. Yes, you'll realize a performance gain, but it's limited by the amount of your program, which is serial only in its nature. So let's take a look at this dichotomy between so-called user-level threads and kernel-level threads. And so user threads are managed by user-level thread libraries. So this means they act like programs running in user space, just like any other piece of software. And there are three main threading libraries: the POSIX threads library, or pthreads. Windows has its threading library, and Java also has its threading library, sometimes called green threads. Now, there are kernel threads as well that exist and run at the kernel level, so they run and are able to execute privileged operations. And so virtually all general-purpose modern operating systems, Windows, Linux, Mac OS, and Solaris is a Sun Microsystems product, they all support kernel-level threads. And so kernel-level threads see all of the resources of the machine. They're run in privileged mode, and they can execute privileged operations, these particular instruction streams. And the user-level threads are in user space and therefore cannot execute privileged instructions. The kernel threads have a quicker context switch because they're supported by the kernel without having to use traps to go back and forth across the scene. So let's take a look at multi-threading models. Now, there are three major flavors of multi-threading. One is called many-to-one, one-to-one, and many-to-many. So in many-to-one, you have one kernel thread. So that's a unit of schedulability or execution of instruction streams supported by the operating system kernel, and therefore has access to privileged instructions. And so there's one kernel thread, and there are many user-level threads. And so these many user-level threads are each given time carved out of the time delta t that the kernel thread has on the CPU. And so what this means is that if one of these user-level threads calls a blocking operation, like reading from a network or reading from a disk, that causes it to want to join the wait queue associated with some I/O device, well, from the perspective of this kernel thread, it's executed a blocking call because some of its time is being given to this user-level thread. So that blocks the entire kernel thread and therefore causes all of the user-level threads in user space to block. And so what this means is if you have multiple user-level threads, now this, you want to make sure this is user-level threads. If you have multiple user-level threads, they may not run in parallel, because if one blocks, that means all of the threads block, because that one blocking thread means the underlying kernel thread is also going to block. And so very few systems use this model. It was an early model of threading, and one example is Solaris green threads and also GNU threads use this many-to-one approach. Why? Because it was easy, right? You didn't have to add or make any special changes to the operating system kernel in order to implement these many-to-one thread models. There's just a library call. All right, so there's also one-to-one thread mapping. In this, we have for each individual kernel level thread, it's associated with a single user level thread. Now this is kind of nice because this is the most concurrency you can have if you have support physically on your architecture, your CPU, having multiple cores with threading implemented on each core, or so-called core threads, then these kernel threads will physically run in parallel, right, at the same time, physically at the same time. Otherwise, these kernel threads will be concurrently making process as they share fractional amount of time, switching from the first thread to the second thread to the third thread to the fourth thread, back to the first, second, third, fourth, etc. on a CPU if it does not support kernel level threading, multiple kernel level threads. And so here, a user level thread creates a kernel thread because it's an application that's creating a thread, and there's one user level thread associated with single individual kernel level thread. And so this offers more concurrency than the many-to-one that we saw on the previous page, and the number of threads per process are sometimes restricted. And the reason for that is you don't want one process to sit there and allocate, say, 1,000 threads if each of those user threads is associated with a single kernel thread, because you're going to end up grabbing up a lot of resources in the kernel thread. And so some examples of this is Windows Solaris 9 and later. So Sun Microsystems was very early in support of threading. In fact, they were doing a lot of interesting stuff back even in the mid-90s that you were just reading about in operating systems textbooks. Happy to talk about that at another time. And then there's lastly many-to-many thread models. Now with many-to-many, you have some number of kernel level threads, let's call that M, and then you have some number of user level threads, let's call that N, and now you have M kernel threads supporting the scheduling of N user threads. Now certainly M does not have to equal N, and there's no prescription that says 2 to 1, the relationship between M and N, but you tune this based on the amount of resources that you have available. So what does this do? It allows many user level threads to be mapped to many kernel threads, and now you can allow the operating system to create sufficient number of kernel threads. And so now you can set a budget and you said, okay, well, I'm going to give 2 units of instruction stream scheduling and run and execution of instruction streams to some user level process. So you say, okay, well, your pool of available kernel threads is going to be 2, or maybe your pool of available kernel level threads is going to be 3. Do what you want with it from the user space. And so in this case, the operating system, it's allowing the operating system to create a sufficient number of kernel level threads. So you're bounding the number of kernel level threads, and then you're saying, okay, go ahead and take your budget of kernel level threads and use that to manage some number of user level threads, and you have complete freedom with the user level threads. And so certainly there's something called Thread Fiber package in Windows that does exactly that. Okay, so that's all for now, and we will continue next time with thread libraries. And again, please make sure you're keeping up with the reading. The reading has changed, so I will end there, and I will see you on Thursday.